Okay. Well, thank you very much for setting this up. This is the and thank you everyone for attending. This is the second of our webinar series on hosted by the Energy Research Centre at the Ryan Institute at NUI Galway. And today our speaker has been invited by Dr. Brian Ward. So the way we normally do, or the way we have done these in the past, is that I would introduce the host, and then the host will give a more detailed introduction to the speaker and the research area. So I'm going to introduce Dr. Brian Ward, who is one of our colleagues here at NUI Galway. He has got expertise in air-sea exchange of carbon dioxide, heat, momentum, and fresh water. The air-sea exchange is constantly occurring, and that governs both weather and climate. And understanding this process is essential to improve the prediction of climate modeling capabilities, and accurate measurements at the air-sea interface are fundamental to this. But measurements of this dynamic interface is a major technological challenge. So Brian has developed instruments for studying upper ocean turbulence, air-sea fluxes, and surface waves. As a result, he has a synoptic view of how the ocean exchanges with the atmosphere by making observations on both sides of the air-sea interface, in air and in water. This has led to new insights on how the ocean and atmosphere interact or impact each other, and how these two fluids operate independently. So I'll hand over to Dr. Brian Ward, who'll give a more detailed and hopefully more informed overview of what we're going to be talking about today. Brian.
Thanks a lot, Rory. So yeah, it's very nice to be able to invite Alex from Dalhousie University. I spent half a year at Dalhousie on a sabbatical, and I interacted with Alex during those 6 months. We did fieldwork together, and we spent a lot of time interacting with regard to our common interest, which is turbulence. Typically for me in the open ocean, but for Alex, as we'll hear today, it's in tidal environments. And so a little background: Alex received his BSc and MSc degrees from the University of Western Ontario and a PhD from the University of British Columbia. He moved to Dalhousie in '96, I believe. He had spent some years previously at Memorial University in St. John's. And he's currently a professor of physical oceanography in the Department of Oceanography at Dalhousie. His research interests include continental shelf and nearshore processes, with an emphasis on sediment dynamics and turbulence, and in the development and use of acoustic remote sensing systems for investigating ocean dynamics of scales from 1 centimeter to 100 meters. Alex is a fellow of the Acoustical Society of America, and today he's going to provide an overview of some of the research that's been going on. Of course, the Bay of Fundy is the ground zero for all the tidal energy development, because they have the biggest tides in the world. And so some parts of the Bay of Fundy, they have up to 16 meters with tidal velocities of up to 10 meters a second. And so this makes it the kind of environment that device developers for tidal energy are looking for. And so many companies have flocked to the Bay of Fundy to install test devices. And so Alex has been involved in some of the research around these devices and providing some input towards the getting a handle on the environment and what's required. So I think rather than me continuing on, I'll just hand it over to Alex, and very much look forward to his presentation. Up to you, Alex. Thank you.
Okay. Thank you, Brian. And maybe I could just ask, how do I get rid of this bar across the top of the display here? Or maybe you don't see it.
So we don't see it.
No, we don't see it.
Excellent.
I think that's just on you.
Okay, good. And you can see my mouse.
Yep.
All right. Well, first, thank you very much for inviting me. I will try to share some results that I hope will be of some interest to people attending the webinar. And as Brian has indicated, I know knowing something about acoustics, knowing something about turbulence. About 10 years ago, I got dragooned by a former student into this, let's just call it, vortex of tidal power development, motivated by a desire and general interest in trying to see how to help the industry develop systems to extract energy from these high energy environments. And what you're looking at is a life ring here. Of course, you see a whirlpool, and you don't see in the middle of the ring an ADCP, you know, a $50,000 instrument that is about to get sucked below the surface of the ocean. It did pop back up, so we didn't lose it, but there was a moment. And this is one of the things that sort of devices that we've been using to study turbulence in tidal channels. And so next slide, here we go. All right, Nova Scotia, I'm here in Halifax. This is the Bay of Fundy. This is the Minas Basin and Minas Passage, where the highest tidal currents are. And just to blow up that area, right here is Minas Passage with flow speeds up to 6 meters per second. I've never seen 10, but you know, maybe they get that high at times. And that drifter that you saw was that it was in this tidal race right here at the end of Cape Split. There are these other tidal passages down at the southern entrance to the bay, Petit Passage with here 4 meter per second speeds, and Grand Passage with 3 meters per second speeds. And these areas are under study, have been targeted for small scale tidal development, with the Minas Passage, the large scale point of interest. And so I'm going to show you work doing down here, but also some. Next slide. Okay. So Brian suggested that I talk a little bit about recent developments in the tidal industry in Nova Scotia. And this is an attempt to do so, focusing on the small scale tidal development areas. And sustainable marine energy is one of the companies that we've been working with, and Nova Innovation is coming online. So if I just click here, sustainable marine energy, this is in Grand Passage, has developed 2 floating turbine systems. This is a second generation one down here with 6 turbines in a linear array. The original one, which was towed over, having been tested in Scotland, to Nova Scotia and reassembled. I guess it wasn't towed over, it was reassembled. Has 4 turbines. And they're 4.6 meters in diameter and generate 280 kilowatts. This guy here, so-called Plat I 6.3 for the 6.3 standing for the diameter of the turbines, generates 420 kilowatts. Importantly, these are floating turbine systems, which has a number of advantages that people in the audience will be familiar with, and which I'll touch upon a little bit later. Primarily in this sort of experimental phase, being able to access the turbines for maintenance. this bigger platform is going to be deployed in minus passage this year. Nova Innovation is going into C passage with 1 turbine this year, and they're going to be installing 15 turbines in Petit Passage in the next 5 years. So things are moving forward. Companies are having difficulty with, I should just add, here's Nova, and it's a 100 kilowatt turbine, which is bottom mounted. So as I say, things are moving forward, but they're coming up against a hurdle that has been placed, a roadblock really, by federal regulators, having to do with being able to assure that there's no impact of their devices on ecosystem, particularly fish and marine mammals. And so that's, being able to do that is with some assurance, is really, really difficult. And hopefully our Department of Fisheries and Oceans will begin to relax a little bit about it. This can go ahead. So an outline of the talk for today, I'm going to talk about turbulence measurements with bottom-mounted ADCPs. There were 2 types of bottom-mounted ADCP, divergent beams and convergent beams. So with divergent beam ADCPs, we can get estimates of second-order turbulence quantities. The idea behind the convergent beam is to be able to get at the higher order statistics, things like kurtosis. And I'm going to present some work that we've been doing on measuring turbine wakes with the drifting ADCPs, getting at the velocity deficit in the wake and turbulence intensity in the wakes. And maybe, I actually don't have a slide on future directions. I actually forgot to take that out, but I might talk a little bit about future directions. So here's a cartoon of an ADCP with, which would be the standard 5-beam variety ADCPs that we have now. So there's a transducer 1, transducer 2, transducer 5 in the middle, and transducers 3 and 4 would be in the plane perpendicular to the screen. And each of these guys transmit and receive backscatter as a function of range in the direction in which of their acoustic axis, and the backscatter, the phase information in the backscatter is used to extract velocity. And I'm using W as my vertical velocity component and U as the in-stream horizontal velocity component. And so V1 and V2 are, these slant beams are linear combinations of U and W, the horizontal velocity, and these coefficients are just a function of the sines and cosines of this angle, depression angle of the beam relative to the vertical. So we get the fluctuations come out of that directly after subtracting the time mean. And if we assume that time averages are horizontally homogeneous, did I spell that correctly? No, homogeneous. Okay. Apologies for that. So here we have the variance of the beam velocities, which involves the cross term, each of the Reynolds stress.
Have we lost
the
signal?
Yeah, only the Reynolds stress, the signal, yes. Provided we can get an estimate of sigma W. And that's what the 5th beam allows you to do. So with 5 beams, you get the full covariance matrix, or Reynolds stress tensor, all 9 components of the tensor. And of course, you can do this spectrally and get it as a function of frequency. So that's the idea. And this is an example of a spectrum where the horizontal axis is radians and the vertical axis is the spectral density. The colors here represent increasing mean flow speeds, in this case, at a height of about 7 meters above the bottom. and the bin interval is about 3.3 meters per second. So the blue is 0.1, and the reddest, orangiest, hottest color is 3.7 meters per second in this case. And in this region, you see a pronounced, a very clear slope, -5/3 slope, which is the inertial subrange, and was predicted by Kolmogorov in 1941. So it's been around for, so this is an indication that the instrument is actually measuring turbulence, with some indication that there's some aliasing up here at the higher wave number and smallest scale. So from the magnet, the spectral density in the inertial subrange, we use the spectral density is proportional to k to the -5/3, with this little guy out here, which is the turbulence dissipation rate, which Brian likes to measure using shear probes, and so do we most. So this is the spectral method for estimating turbulence dissipation rate, given that inertial subrange. And we wanted to test this idea, and Millen, a doctoral student who worked with me a few years ago. So we mounted shear probes in the nose of this streamlined float, which was anchored to the seafloor about 10 meters above the bottom, with an ADCP on the bottom nearby. And the gray points represent individual estimates of turbulence dissipation rate from the shear probes in the nose. If you don't know what a shear probe is, it doesn't really matter. We can talk about it later, but basically it's just a little device about the size of your fingertip that wiggles due to the velocity fluctuations in the flow going past it. And the magnitude of those wiggles is transferred to an electric signal via a piezoelectric element. So the blue dots represent the average of all the individual estimates from the shear probes. And they follow in this log-log plot. I haven't shown it, but this slope is the cube of the velocity. So I'm sorry about that. So the red line is best fit using 2 velocity cubed. And these squares are estimates from the ADCP, the nearby ADCP. So they follow the same line, but they're off by about a factor of 2. They're different by about a factor of 2. And we thought about this and worked on it for a long time. And we decided that was most probably due to the fact that they weren't in the same place. But the takeaway message is that the acoustic estimates of dissipation rate are within a factor of 2 of directed measurements using probes that are traceable back to the library, to a laboratory standard. This is an estimate of Reynolds stress from the diverging beam ADCPs plotted against U star estimated from the vertical profile of velocity, assuming that the log of the wall is valid. And these are the dashed line is just a one-to-one line, not an attempt at the best fit. And the takeaway message here is that the estimates of Reynolds stress from the ADCP, the U prime, W prime term in the equation that I showed before, is the same as the estimate from the vertical structure of the horizontal velocity near the bed. Now, turbulent kinetic energy, which is what I want to talk about next. So again, I've shown profiles of flow speed with up to 4 meters per second near the surface. And again, these are averaged in speed bins of 0.3 meters per second width. And I haven't shown them all. There are actually more bins, but just for clarity, I haven't shown them all. And this is the dashed lines and solid lines distinguish the decelerating and accelerating phases of the flood tide. So, so the tide is at the onset of flood, water levels are low, so we are in minus passage, and the water level is changing by 10 meters during the course of the tide, and water level increases, so the velocity profiles extend farther away from the bed, and then continue to extend farther away from the bed as the water continues to flow in the decelerating phase of the tide. And so that's just distinguishing the what the meaning of these dashed and solid lines are, providing context. And this is the turbulent kinetic energy estimated from the slant beam ADCPs, which decreases, well, it's intense near the bottom because the turbulence is generated mainly at the bed, and decreases toward the surface. And if we scale the turbulent kinetic energy, square rooting it, scaling it by the mean velocity at each height above bed, then it provides, you see as a standard rule of thumb that, well, the turbulence intensity or the RMS turbulent velocities are about 10% of the mean flow velocity. But they are much higher near the bed, up almost up to 15%, and lower than 5% of mean flow closer to the surface. So this is an argument for surface-mounted turbine. The flow speeds are higher, the turbulence is much reduced, and that's a known thing, but it's nice to see it in the data. But, well, second order quantities, well, what about how big do the individual fluctuations actually get? Do we have to worry about instantaneous turbulence measurements? So here we are with a system that we have developed in conjunction with FORCE, the Fundy Ocean Research Center for Energy in Halifax, which we euphemistically call, or fondly call the Vectron, or not so fondly. It's a wide baseline ADCP with converging beams. So the beams all converge in a 2 to 3 meter depth interval, about 10 meters above the bottom. They're mounted on this big frame with a 6 meter separation between individual transducers. They, with an opposing pair again into the page. And if we think of this as being beam 1 and this is being beam 2, the center beam in red, beam 5, transmits and receives. The outer beams just listen. So in this overlap region, at little depth intervals here, this stack of coins represents each range cell. The system estimates the instantaneous values of the 3 Cartesian components of velocity after converting them to from beam coordinates to so this is an expression indicating that. So now we have our 2 beams, 1 and 2, which involve linear combination of the vertical and horizontal velocity fluctuation. And so instantaneously now we get estimates of the horizontal velocity fluctuation and a vertical velocity fluctuations, where the 1 and 2 represent the fact that this is an estimate from that beam pair. We also get an estimate from the other beam pair and the orthogonal component of the velocity. And then, of course, W5, the 5th beam, gives us 3rd estimate for vertical velocity. So that's in theory, and now these are what the results look like. So remember, the motivation here is to get at the distribution of these instantaneous velocity components. And we just expect them to be Gaussian. And so this is a log plot of normalized velocities normalized by the standard deviation, sigma, horizontal and vertical component. So horizontal on the left and vertical component on the right. The black line is a Gaussian, which is not a fit. It's just a Gaussian with the same standard deviation as the data. And the fit is quite good. K is the kurtosis, which would be 3 for a Gaussian. And it's very close to 3 for both vertical and horizontal velocity components. And this is for velocities in the range here of 0.3, 0.6 meters per second relative to 3 during this plot. The black circles just indicate that these points have less than 10 estimates in them. Okay, that's good, but the reason that we did this, went to the extent of building the Vectron, was because of, excuse me while I have a drink, because it's a known fact that turbulence is intermittent. And these are results from the atmospheric boundary layer in a very famous paper by Banata and Chen in the Journal of Fluid Mechanics in 1970, indicating how non-Gaussian the velocity differences are. So, or in this case, just the derivative velocities divided by sigma. And so at about 3 sigma, the velocities depart from a Gaussian, and you have these heavy-tailed distributions with and peakier peaks. So high kurtosis. And this is associated with the fact that turbulence is concentrated in little spots, if you like, and therefore at a measurement point, as they're advected past, there's these patches of high dissipation rate. Another way of looking at it. So this has also been done over ground, most recently in a paper by Wachter et al., and where they were taking measurements made from a wind turbine mast at an elevation, I think, of 100 meters above the ground. I may be wrong about that, but again, at a sigma of about 3, so 3 standard deviations away from the mean, the distribution becomes heavy-tailed and peakier in the middle, for 0. Now, and they made the point that this is 10 orders of magnitude greater than would be predicted by Gaussian statistics, and raised the concern that this would have for the stresses on turbine blades. All right, so what does it look like in minus passage? Well, it turns out that the horizontal velocity component is still, the differences are still quite Gaussian. And what I plotted here, velocity difference at the smallest value that I could get with the data that I have. And I'm losing my connection. Can you hear me? Ken?
Yes, we can. We can.
Okay.
It occasionally slows down, but only very occasionally.
Okay, good. So I'm about 3/8 of a second away is the smallest time difference that I can estimate, and the kurtosis is shown here. It's still very low. However, the vertical velocities are heavy-tailed. They're not peaky, and the kurtosis is about 0.7, so quite different from 3. And they become heavy-tailed at 3 sigma away from the mean, more or less. So what does this mean? Well, why are they not peaky? Why are these velocities, the horizontal components, not showing any heavy tails? I don't think we really know, except I have guesses. I think that the horizontal velocities, which are intrinsically noisier than the vertical velocity estimates, are what is preventing the vectron from resolving the kurtotic behavior, the heavy tail behavior in the horizontal velocity components. And I think similarly, the noise in the turbulence estimates is preventing us seeing the peaky behavior at low values of delta of velocity difference. But those are speculations at some point. And then the question becomes, well, what does this tell the industry about? Do they have to worry about these heavy tails or not? And that's not really for me to answer. I'm really not a turbine engineer of any. I'm a physicist. But I'm thinking that this behavior is appropriate for the scales at which we measure turbulence with the vectron, which is like 20 centimeter range bins and beam widths of a similar value. So basically, something around the size of a soccer ball is about, or I should say a football. Sorry, you guys and gals. Is the scale that we measure, and then is that what scale is of importance to turbine manufacturers? Okay, this is now the next thing. So we want to talk about these drifting ADCPs that you saw one of in the opening slide. We wanted to measure the wake of plate I1. This is the 4 turbine array. You see these mounting poles, the turbines to which the turbines are attached. You can actually see the bit of a wake from each of the turbines in the near field area. And these are our 2 drifters, each with a 1 megahertz ADCP, 5 beam ADCP, and the light frame. And these vanes here are just to assure that it travels with the surface velocity. Here are some data, and these are data. So I've been working with Marie Carmen Guerra Perez, who was a postdoc with us for 2 years after doing her doctorate with Jim Thompson out at the University of Washington, and is now held a faculty position in Chile, her home country. Here she's shown a map during ebb tide of the vertical velocity fluctuations, the mean square fluctuations in vertical velocity, colored by the magnitude of that. And these C high regions. So this is the X is the location of plate I. We're looking at horizontal scales of 200 meters across and 300 or so meters downstream of the platform, and high turbulence intensities in the inner part of what we're calling, I'm going to say is the wake, and the dissipation rates are also higher in the wake. We now have much better measurements of this stuff from measurement work that we did last year, but I don't have those maps. More interesting perhaps than these are the profiles of mean velocity as a function of downstream distance from the platform location. So starting at 60 meters downstream, so in here, and going to 100 meters. So just this region fairly close to the turbine. And what you see then as our vertical velocities of horizontal velocity v in this case, with speeds up to 2 meters per second. The orange profiles are when the turbine was operating, and the blue when it was not operating. And we see the velocity deficit in the wake. I should mention that the dashed line indicates hub height for these turbines, which were 6 meters in diameter. And the magnitude of the deficit decreases with distance downstream, and so does its vertical extent as it mixes in with the ambient flow. So that then allowed us to plot the difference between the velocity at the center of the wake and that average. Oh, what am I? I'm probably gonna get this wrong. Let me just trust me that this is the velocity in the velocity deficit as a function of distance downstream, with the pink arrow here indicating 10 equivalent diameters of the turbines, where the equivalent diameter accounts for the fact that it's a linear array, and the black line indicates that it's falling off at 1 over the square root of distance. The green lines 1 over minus 2/3 of the distance downstream. So this would be the 2/3 exponent is appropriate for a single turbine, and the root dependence, 1 over square root dependence, is for a linear array. So, I mean, the data are noisy, but more consistent with the square root dependence. And the other thing to look at is the wake is basically just not there when the turbines were not operating. So one of the serendipitous things that came out of this work was the difference between the behavior of the turbines and the wake when they're fouled and clean. So the platform had been sitting out there unused for months, a few months, and this stuff collected, I shouldn't say unused, not operating, and this biological material accumulated on the rotors and on the faired strut, and was cleaned off with a power washer. But before it was cleaned off, they actually did some runs, and the experimental data of thrust versus flow speed from the company, in this case Sustainable Marine Energy, shows the thrust versus flow speed curve for the fouled blades is the yellow, with the dashed line being a boundary element model and the points being the observed values. Then the cleaning took place in 2 stages. First, the power surface was cleaned, and then both sides of the blade were cleaned. And the model was run for both cases, and it shows the increase in thrust for clean blades relative to dirty blades, foul blades. And serendipitously, we had estimates or measurements in the wake for both conditions. So for clean blades, there's a very clear velocity deficit. For the dirty blades, the foul blades, there is a deficit, but it's much, much weaker. We're carrying on these measurements, I should say. They with SME, and that we'll talk about that in terms of future work, I guess. So to summarize, divergent beam ADCPs give estimates of dissipation rate agree with shear probe that are traceable back to a lab standard. The Reynolds stress and log law estimates of stress agree. The turbulent kinetic energy profiles indicate that the turbulence are a bit less than 15% near the bottom and quite a bit less than 5% near the surface. Convergent beam ADCPs, the work we've done so far, indicate that the observable fluctuations in W prime in the Cartesian components of velocity are Gaussian out to 5 plus or minus 5 sigma. The fluctuations in the horizontal velocity component also Gaussian out to about 5 plus or minus 5 sigma. The vertical velocity, the differences in vertical velocity fluctuations are heavy-tailed above 3 sigma. I think that's a nice result to get from this experimental system. And the question is, what importance is it to the industry? The drifting ADCPs using the divergent beam configuration for a 4-turbine array wake give us velocity deficit estimates that persist out to 10 equivalent diameters downstream and a lower velocity deficit due to fouling. And as I said, this work is continuing with much better data. Lots of people to thank. I won't thank them all. I will mention Justine McMillan, I've mentioned, and Marie Carmen Guerra Perez, our former postdoc. I do a lot of work with Len Zadell at Memorial University and Richard Karsten at Acadia. We're doing work with Angus Creech now, comparing our results to his model, Joe Helena at Force, Sven Nyland, and Robert Craig with Nortec. Rolf Lewick and his collaborators at Rockland Scientific, who helped us out with the shear probe measurements, and sustainable marine energy, Ralph Startzman, Penny Jeffcoat, and Jason Carlson, and the funding people and questions. All right.
That was great, Alex. Very interesting. I have a question about the, what was the instrument you called it? The
Vectron?
Yeah, the Vectron, that one. So were you surprised that that you didn't see the level of kurtosis that you would see from say the atmospheric measurements? Or you cited a paper and you showed, were those ocean measurements from the 1971 paper?
Let's go back. I was disappointed, frankly.
You were? Okay.
Yeah. But I can rationalize it without going into a lot of detail. So we know that kurtosis appears because of dissipation being spotty in space and time. And that occurs at the smallest scales of the turbulence, which we don't resolve and can't come close to resolving with these acoustic systems that we have because of their limited spatial resolution. and also the limited temporal resolution. So it's a double whammy in that sense. It's I mean, you know, and everyone familiar with this knows that in order to get these high values of kurtosis, you have to sample very rapidly and at high resolution. So I think now, after the fact, I'm not surprised.
So do you think your signal was earliest because of the inability to resolve all these scales?
Yeah, I mean, if we go back, I mean, I should have a cartoon to do this. But okay, so here's a spectrum. And these are, I'm pretty sure, you know, the radian wave numbers. So, you know, this is the minus 5/3 range for this, you know, Kolmogorov microscale is way down here, way off the page.
Yeah.
Yeah, because we're looking at dissipation rates. We could do it in our heads perhaps, but I'm not going to be able to. We're looking at dissipation rates of about 10 to the minus 3 watts per cubic meter, watts per kilogram, I'm sorry. And so it's a tiny microscale.
Yeah.
So we're really only seeing the very top end of the subrange, the inertial subrange.
And the other question I have is related to that. There's a significant difference in the turbulence between the bottom and the surface, and I guess that's just that turbulence near the bottom is just interaction with the bottom of the tidal channel.
Indeed.
Or is there faster flows? There's faster flows as well.
Well, no, it's so there we are.
Oh, no,
no,
it's the opposite.
So that's right. So it's friction at the bed due to so it's sucking all the momentum out, and the turbulence is transporting the momentum to the bed. So so this is just a function of the fact that turbulence is generated at the bed, and the vorticity diffuses upward, and extracting momentum from each, you know, progressively the higher it extends above the bed. So it's that fact that, you know, in terms of relative to the mean flow speed, the velocities are low down here, but the turbulence is high. So that's why the ratio is much higher.
Yeah, right.
Yeah.
And if I recall, the open hydro turbine was a bottom-mounted turbine.
It was indeed. It's still there.
It is.
I would have, but I didn't really want to. I would have brought an imaging sonar image of the open hydro turbine. But I know that open hydro might be a bit of a sore point in Ireland, so I didn't want to hit that button. But since you raised it, we can talk about it. Yeah,
sure. So I mean, I know they had a lot of issues, but given that they were deploying a turbine at the bottom, doesn't sound like it's the right place to be if you want to avoid turbulence. So the SME turbines, which are, you know, just below the surface, I imagine, and they're floating, they move up and down with the tidal range. So it seems like that's the right place to be for.
Well, I mean, there are other things that go on. You know, the attraction of the bottom is that it's, you know, the turbines are then out of the way of navigation, out of the way of ships, so they're not a navigation hazard. which is a significant issue. And also at the surface, depending upon the tidal channel you're talking about, waves can be a big deal.
Right.
So there, I mean, each approach, I think, definitely has its merits. I think, you know, maybe Open Hydro tried to go to the, you know, the highest, one of the higher energy tidal locations in the world. And it's we don't have, you know, what is needed by the industry is really significant infrastructure for recovering, deploying, and maintaining these systems. And you know what it looks like for wind farms. There's going to have to be something at that level developed for tidal energy sites, I think. But there's a lot of money required to do that.
Right. We have another question here from Sheena. Sheena asks, was the mooring system used a stable moor system from deep water buoyancy? Did you find it behaved well in the flow and kept the ADCP physically stable? So I guess she's
well, that is such a good question. Yes, it was the stable moor. And to make a long story short, we deployed it. We had planned on 2 one-week deployments, and the first deployment just being a test to see how it would behave, and the second week being the one in which we installed the shear probe. Well, we deployed it the first time and said, "Oh, hello." It floats nose up. I think the tilt angle was something like 70 degrees relative to horizontal. And that led to a mad scramble, including driving around to the southern tip of Nova Scotia to a shipbuilding place to get a 40-pound lead pig and strapping that to the nose of the stable moor. So it would, so it behaved well in high flow. But I've been, one of the things that if I ever do it again, I will modify it so that I have an adjustable pivot point, and kind of yeah. So it was, the answer is yes, it did behave well, but it tended to behave better at high flow speeds, which was what we were really interested in. Yeah.
All righty. I don't know if there are any other questions. It doesn't seem like there's anybody else in the audience who's
okay.
Sending in questions. So
sorry, Brian. I was speaking into the void there with my mic turned off.
Okay.
Is there, and so I'm coming at this from a mechanical engineering, mostly modeling based approach. And are there simulation efforts underway that you're aware of, Alex, to sort of try and, you know, match what you're doing and try and maybe develop some further insight using you know, LES turbulence models and various things like that?
You hear anything?
Oh, sorry, it went quiet for a second. I can hear you again.
You're asking, so when you were asking about simulation efforts, but in regard to what? Sorry,
well, I guess in generally in regard to the Bay of Fundy, you know, thinking about the, you know, the renewable energy potential that's there, and is there any sort of tie-in with modeling efforts to the sorts of measurements that you're making? I'm not sure if the block is on my side.
Hear me, I'll talk about simulation efforts that I'm aware of.
Okay, great. Yeah.
So SME is simulating the response of its turbine to turbulent fluctuations in the flow. And I don't know a lot about the details, but I do know that they are finding that turbulence, the presence of turbulence, seems to increase the power output from their turbine. So that's at the turbine scale. At the, you know, in terms of the ambient flow types of things, I'm very keen on working with people who are developing large eddy simulation models of turbulence in these channels. And Angus Creech who's now moved to Nova Scotia from Scotland, is someone that we're working with, and he has a very nice model which he's keen on validating. And so that'll be work that's ongoing this year. We've been working with people at the University of New Brunswick who have also developed what they call a detached eddy simulation model of flows in these channels, and we're comparing our results to theirs. That work is sitting in the hands of a couple of postdocs who are supposed to be writing it up, and you know, it's kind of out of my hands a little bit. but then I'm not all that quick off the mark in getting things published either. So there's all this stuff with the Vectron which we haven't published yet.
Fair enough. Thank you.
All right, Alex. I think that we've taken up enough of your time for today, and we'd just like to thank you very much for giving us this very interesting seminar. I mean, tidal energy is something that's of great interest. I noticed that the second company you mentioned, was it Nova Innovation?
Yes.
There was a little Irish flag on it, so there must be some Irish participation there, presumably. Maybe there were some of the guys from Up in Hydro who transferred over.
Maybe, you know, I don't know what that connection is. I think they started out up in the Orkneys.
Okay.
Yeah. So I didn't notice the Irish flag. Sorry.
Okay, no problem. So, well, this is again hosted by the Ryan Institute. So we'd like to thank you very much for giving a very nice talk, and hope to see you soon. If you wanna stick around, Alex, we can have a chat afterwards when everybody signs off.
Okay, will do. Thank you very much. Thanks
Yeah.
to the audience.
Thank you.